Hey guys, we're here in the last section of Chapter 8, which is also the last section before the second test. It's 8.4 on trig integrals, and so I've recapped here what we know from the last section, the derivatives of sine and cosine. So when it comes to antiderivatives, in this section, all we're focused on is sine and cosine, and simply because they're the simplest of the derivatives, and then so the antiderivatives as well, but also because every other trig function is based on sine x and cosine of x in one way or another. So it all comes back to one of the two. And so we can do quite a bit with just these derivatives and antiderivatives. So, okay, so you see here we've got derivative of sine x is cosine of x. And we also learned that the derivative of cosine x is negative sine x from 8.3. So what does that mean? Well, we can work backwards, right? So the integral of cosine x dx must be sine x plus c, working backwards. And here, the integral of sine x dx would be negative cosine x plus c, because if you take that negative off, well, then the negative would have to move onto this side, right? So to move back, you've got negative cosine going the other way. So what are problems going to look like? Well, we'll have definite and indefinite integrals, mostly indefinite integrals, just working on the antiderivatives. Pretty much everything we're going to see is going to need a u sub, and that's just the nature of working with trig integrals. You see a lot of u substitutions. So when you see something like antiderivative of sine 4x dx, you say, okay, I know how sine works backwards, but how does it work if it's sine 4x? Well, you might be comfortable enough just to do that antiderivative immediately if you can see how that's going to work backwards against the chain rule. But if not, hey, that's why we have u substitution. So what are we going to make our u here? Well, to make it simpler, right, we can just set u to be the 4x, and I don't want to reveal too much, so I'm going to cover this up. So if u is the 4x, then our du, of course, is 4dx, and we don't want that 4, so we're going to divide it over. We'll make the dx 1/4 du. So pretty simple when you see it. When you put it in on the other side, I've started it right there. That's a 4, by the way. Okay, so we've got the sine of u, and the dx turned into 1/4 du. And, we can move the 1/4 to the outside, and then finally take the antiderivative of the sine to be negative cosine of u. And finally put your u back in for the final answer, negative 1/4 cosine 4x plus c. Great way to check your answer is to take the derivative, but we can kind of see that, right? The derivative of cosine is negative sine, so that would cancel out this negative, bring it back to sine, and then we'd have a chain rule. We would need to multiply by the derivative of the 4x. That would cancel the 1/4, and okay. We can see that. Now, this is the simplest example I have, but as I said, they're all going to use u sub almost every question. I shouldn't say every question. Almost every question is going to use u sub in this section, unless it's simply sine x or simply cosine x. And you do to get a couple of those actually with some definite integrals and some of the applications. Okay, how about this one? Integral x to the third times the cosine of 2x to the fourth plus 1. I think, well, that's really just a more difficult version of the one we just did with sine. And so, hey, what if I make what's in the parentheses my u, right? It's typically what happens. What's in the parentheses? So that would make my du, right? 8x to the third dx. And I don't want that 8, so I can divide the 8 over. So my x to the third dx becomes 1/8 du, and here I'm going to go for it. I'm just going to go ahead, because it's so similar to the last example, and we've done, hopefully we're very familiar with u subs. I'll just take that 1/8 all the way to the front, times the cosine of u du. Antiderivative of cosine is sine. Now, students tend to get mixed up on the negatives, right? The derivative of cosine is negative sine, but the antiderivative is just sine, because if you think backwards, the derivative of sine would simply give you cosine. So I would say write it, and then it's people tend to remember the derivatives more than anti. So check it back this direction. Yep, derivative of sine is cosine. And then plugging my u back in, there's my final answer. 1/8 sine of 2x to the fourth plus 1 plus c. Again, a very similar chain rule, right? To get back to the original. And no harm in checking that even with all the steps if it's difficult to see. Okay, we're moving along well. Part C. Now we're getting a little bit harder. This one is a definite integral. 0 to pi over 2 sine x e to the cos x dx. All right, well, one thing I should point out just here at the beginning, we'll say it when we go to plug in the 0 and the pi over 2. Definitely want your calculator in radians. Whenever we do calculus, we always think of the angles as being in radians. We won't ever use degrees there. Turns out that the rules for the derivatives, the fact that the derivative of sine x is cos x and cos x is negative sine x, those are based on the x being an actual length, a radian measure. The derivatives would actually be different if they were degrees, and I won't go into it. But we really like those very simple derivative rules for sine and cos. And if we think of it as degrees, it would be a little bit more difficult. Okay, anyway, point being, b in radians. Here we've got this integral. Well, it is going to be a u sub, and I'll just put it out there. What should we make u? And how about this even? If you feel like taking a crack at this problem on your own, go ahead and pause the video here. I'm going to keep going in a moment. I'll give you a chance. Pause the video. Try this one out on your own. And if you want to, even after you do the antiderivative, plug in the limits. See if you can get to the final answer. But I'll go ahead with it right now. Okay, so what are we going to set as u? And if you said, well, the inside here is really the cos, then you're right. It's up in the power of e. We're going to make u the cosine. There might be some experimentation here, right? If you made u maybe the sine, and be like, oh, there's no way, like I can't, it just won't quite fit. But if you make u cosine x, then your derivative is negative sine x. Of course, we don't want that negative, so we pull it out, and then we can rewrite this thing very nicely. The negative I just pulled all the way out to the front. E to the u, where the cosine was, of course, the sine x dx just became that du. And doing an antiderivative of e to the u works out pretty fast. And we come to here, put our u back in. Negative e to the cosine of x, right? From 0 to pi over 2. And now it's really important that we use radians when we plug in. Well, I guess I just put the numbers in like this for now, cosine pi over 2 and minus, okay, cosine, there we go. And now this is where I officially note it. So grab your calculator at this point, put in the cosine of pi over 2. If you're in radians, you should get 0. And the cosine of 0, you'll get 1. Negative e to the 0 plus e to the first. The final answer here is negative 1 plus e. Actually works out really nicely. It looked pretty bad at the beginning, but it plays out well. Okay, so maybe you're thinking, all right, I see that, but, you know, maybe kind of like to see the other side, what if we had made u sine x? Like, what would be so bad about that? I kind of mentioned that sort of quickly earlier. Well, at first, maybe it seems like that's okay. I mean, du would be cosine x dx, right? But then how's it going to work? Because, you know, if the sine becomes u and this cosine is up in the power of e, right? It's not being multiplied by dx, it's up in that power. We're just not, that this just doesn't fit. I just can't get that to work. So because cosine is up in the power of e, that tells me that I need to pick for u, and now the rest of it can become du. So certainly some trial and error is okay. And some of these, it might be, maybe this one, you know, was clear to a lot of people why we should pick that, but maybe other ones not so much. Turns out I've only got one more example for us in this section. These sections are quite brief, it turns out. Hey, I don't think any of us are complaining. This one can give you some problems. The integral of cotangent x dx. Interesting. All right, well, I said at the beginning, right, the only antiderivatives we know are for sine x and cos x. So what are we going to do if they throw us something like cotangent x? You've got to remember at the first step that cotangent x can be rewritten as the cosine of x over the sine of x. That's based on the fact that tangent x is sine of x over cos x, and of course cotangent is the reciprocal, so we flip it over like that. Okay. Well, at least we're looking at cos x and sine x now. We're going to have another u substitution, but how exactly is it going to work? What are we going to pick for u? Should we pick u to be cosine x like we did last time, or should we pick u to be sine x? And it really comes down to like numerator versus denominator. And again, there can be some trial and error. Really, honestly, it would be much better if we had this conversation in class and we could try out one way and try out the other way. I guess we can do that in the video, but there's not much back and forth, right? It turns out in this case, we want to make u whatever the denominator is. And I'll just kind of show you my work there. There's nothing else going on, so if u equals sine x, du is cos x dx, and I need that because I need my du to be the product of that derivative and dx, and that's what I have, right? The dx could move up into the numerator, cos x dx. So all of that there and there becomes du, and I'm looking at 1 over sine x, right? 1 over u du. And just to get to this far, right, to notice this substitution, to be able to rewrite it this way, I mean, that's the whole problem. I mean, that's the difficult part. Those two things. But once you have it here, well, what's the antiderivative of 1 over u? And probably something that we're pretty familiar with. Hopefully that's the natural log of u plus c. And we can go ahead and put our sine x back in there, and we got it. The natural log of sine x, technically the absolute value of sine x, plus c. And there you go. You could check the derivative here. right? It would be 1 over sine x times cos x. And then the cos x you can think of going back to the numerator, you'd go back to cotangent x. Well, it turns out this section was just the one video. This is everything. There are going to be some applications in your homework, but you know, they really are very straightforward. So like the most difficult questions are these where the tricky use substitutions. So that's what I wanted to highlight. And hey, we can talk about anything in the live session. So I will see you guys there. Good luck with the homework.